Hello and welcome. This class will focus on structural integrity and multi-die system design. In today's electronics, the mechanical reliability of stack design is just as important as their electrical performance. We'll begin with key mechanical concepts, then explore how thermal effects shape structural behavior across multiple design levels. And finally, we'll walk through a real-world example, a HBM system, to understand practical design and analysis approach of structural integrity. So, what is structural integrity? It is a structure's ability to resist failure, whether from stress, deformation, fatigue, or collapse, under expected operating conditions. In the context of multi-die system design, structural integrity hinges on mechanical stresses from temperature shifts, packaging constraints, and external forces. The material reliability in interconnects and solder joints, the resistance to cracking, delamination, and warping during manufacturing process or operating conditions. So temperature changes can alter the shape and size of a structure. This is called thermal-induced deformation. Typically, we use the strain tensor to represent displacement across an object's geometry. The amount of deformation depends on a factor called CTE, or the coefficient of thermal expansion. So CTE defines how much a material expands per degree change of the temperature. Then we introduce stress, force per unit area, and strain, the resulting deformation. And Hooke's law actually linked the two parameters with Young's modules as the constant. Together, these relationships help us trace heat-driven shifts all the way from expansion to structural stress. Material selection drives everything in structural integrity analysis. Each substance, such as silicon, copper, solder, in the multi-die system has many properties, such as mechanical, electrical, thermal, chemical, and so on. Some are constant, others change with conditions. So for reliable simulation, we need to characterize these parameters and properties accurately. We sometimes use generic data, but it's better to also use the foundry-specified properties based on their particular process. We mentioned about boundary conditions before. Now, boundary conditions are essential for solving multiphysics integrity problems, especially for structural integrity. They define the constraints like fixed values or initial states of the structure. For example, thermal analysis might use ambient temperature or surface heat transfer coefficients. And mechanical analysis might fix certain surfaces to prevent motion as a boundary condition. Electrical analysis might use input voltage or current as a boundary condition, which set up and help us build a realistic model to build the whole strip system. In structural analysis of multi-die system design, dies are stacked using variable materials, each with its own CTE. So if temperature rises unevenly, the materials expand at different rate, creating warpage and stress. Thermal cycling events such as heating and cooling over time can also trigger permanent deformation and damage of the solder joint system. It can also break hybrid bond and metal layers. That's a serious problem that reliability and structural analysis has to deal with. Now, let us revisit the HBM system design we discussed in another session for thermal integrity. The same design with 8 stacked DRAM dies sit on an interposer side by side has been here as an example. This configuration of multi-die is ideal for exploring the structural integrity and how heat and mechanical stress flow through multiple dies and interconnects. Here, the result of structural simulation help us detect two key issues of the multi-die system. First is the maximum warpage, how much the stack bends, and does that actually beyond some limitation and specifications. The second is maximum stress, the most mechanically vulnerable points. But note, these stress results rely on accurate thermal simulation data as well. The thermal expansion patterns form the baseline for predicting structural deformation, just like the example showing us here. So how do we manage thermal and stress risks of multi-die design? The designers should follow multi-stage co-optimization flow from system planning to tape-out. A shift-left strategy means you have to catch issues early using prototyping model to simulate thermal and structural behavior long before the final sign-off. It is a proactive way to reduce late-stage surprises and costly redesign of the multi-die system, considering maintain all the multiphysics integrity behaviors. So if simulations reveal that any thermal structural integrity problem are there in your multi-die design, what are the responses designer can do? At the device and circuit level, they can reduce power, balance the power density, or even revise floor planning. At system level, they can optimize die and interposer size, routing, and bump layout. They may insert dummy thermal vias or metal fields to redirect the heat. And don't forget, material selection is crucial, especially early in design. At the software system level, they can deploy thermal sensors, heat spreaders, and dynamic cooling solutions. And they can apply voltage scaling and thermal throttling approach. These countermeasures against structural integrity problem work together to manage heat and preserve structural integrity of your multi-die system. To tackle all of these multi-physics challenges, Ansys offers a comprehensive suite of tools. For chiplet-level modeling, Ansys supports signal integrity, power integrity, and reliability analysis. For multi-die systems, Ansys can help customers simulate heterogeneous integration system from early prototyping to final sign-off. At system level, Ansys provides reduced order models to simplify complicated thermal power and reliability data across thousands of components. To explore more, I recommend you checking out the product pages and relevant course materials. And thank you for joining this journey through structural integrity in multi-die systems. We hope it is sparkle new insights into how to design reliably in 3-dimension multi-die system design. Thank you.